personal life too.
Great. Okay. Hello, everybody who is watching the recording. So we'll be going over a few data structures that are common in interviews. These are also covered in most of data structures and algorithms. Oh, wow, someone joined. It's amazing. Hi, Tina. Um, anyway, these are like some of the basic data structures. We're just gonna go over like the basic ideas of them. We're not really gonna go into any like language specifics, although I will mention like a few things, like the way things are referenced in different languages like Python, Java and C++. They're called different things, so it might vary. It's like important to know the differences. And generally, these are just good to know for interviews. These are pretty common. I think I think Andrew Chen mentioned these on about cracking the coding interview, the book. He mentioned this on Thursday. These are some of the ones that I mentioned there that are pretty key. The only one I don't have listed for today is graphs. Graphs are pretty theoretical. They're really interesting. I think they're like, you really need like more time to like look at them. So I'm not going to talk about them too much today, but we can like go into like a very basic structure, like idea of what they are towards the end. So let's go ahead and get started with arrays and strings. So arrays and strings are the most basic data type. It's basically you have a set amount of data types. So for example, in Java, you have an array or a string. You have to have a set number of characters that are going to be in it. So the characters could be chars or ints or any other data type that are available. And the key thing here with arrays and strings is that they are not, I should probably write this down. They are not mutable, they're immutable. So you can't change them after you initialize them. So what that means is like, if I make a new array that's size 8, right? Like a equals int 8, right? Then this thing is only going to ever be able to carry 8 items. But if I wanted to change it, I would have to make a whole new one, um, and then I would have to like copy all these elements over into a new one of a larger size, right? So then if I want to say like, I don't know what to call it, but like if I want to create a new one, basically the idea is like you can't have the same, you won't be using the same data block. It'll be like a whole new structure. You copy all the old elements and then you'll be able to add new elements towards the end. So the cost here is to copy everything. This is weird, but to copy everything, you'll need to take O of n time in order to bring everything from the original array to the new one. That's just because you need to, in order to import everything, you have to go through each one, say, like A0 goes to, say it's called B, equals 16. A0 goes, so B0 is equal to A0 all the way through A7, the final index. B7 is equal to A7. And then after that, you'll have like B8 through 15. Let's say if B is equal to 16, then you'd have that space to like assign elements. That's the downside of these. It's kind of slow, but it is like a set type, so it's easier to understand. And these are pretty common in interviews. I've seen a lot of these just like as a given. And yeah, access time is going to be pretty good, is O of 1, because you're accessing the index directly. So let's say we have a dot, or just like a bracket 2 would get you the element here. Yeah. And strings are just the same thing. They just have chars instead of more flexible arrays. Arrays can be ints or other data types that you want, or even objects. The idea is it would just be, your size times the size of the number of bytes of whatever object you decide to use. So let's say I decide to create an object that's called recipe. Then if I made, let's call it R is equal to recipe array of size 4, because I want to have 4 recipes. this would create 4 blocks. Each block is the size of a recipe. So a recipe could be, let's say, 24 bytes. So this would be, each one is 24, 24, so on. But it's going to be 4 times that is the entire size of R. And then you would be able to reference things through indices. Okay, next, linked list. This is probably one of the more important like base classes you want to know. And at the core of linked lists, you have the node class. And basically a node for a singly linked list, is what we're gonna talk about first, is gonna have its own data type. So let's say, I'm not gonna give it a type yet, just call it data. And then you would have next is gonna be a pointer to another node. And then you would also, I guess you wouldn't really have anything else, but at the core of like a linked list, the object is gonna be, linked list has the head, which is gonna be a node. Everything's gonna be a node. Linked list just has the head, and then you could add other attributes to it if you were to implement your own. The head basically is the only way to access elements in the list. So if you take a look at, let's draw one out. So you have head. So head is a node. So head is gonna have data. So head.data, let's say that is 0. And let's say next. Right now at the beginning, we have nothing else. So it would be none. Now, if we were to add one and change next to node 1, we would have this, you have to create a new node. Go back to silver. I don't know what's up with all these colors. And then basically just have like another node. You wouldn't have to call it anything, but like when you create it, you're gonna wanna have like the pointer to it and then make sure that your head, your previous item points to this new node. So node is obviously another node, and then you give it like your own data type or the data value, and then it'll also have its next because it's a node object. And then this is how you would create them. You just have to make sure you link it from the previous one. So the problem with singly linked lists is that you can't have O of 1 access time as you did with arrays, because in order to get, let's say, the 4th element, you would have to traverse from head through node, through the next one, the 3rd one, all the way to the 4th one. You have to make these steps to get through to it. There's no way to directly access like linked list dot or linked list paren 4 or 3 is, I guess the index would be. You would have to iterate through the entire list just to get to each one. So a problem I was looking at before was if you have a linked list, let's say 1 leads to 2, leads to 3, leads to 4, leads to 5. Let's say you want to remove, you're given the middle one and you're given the pointer to the middle node, and then you want to remove it while preserving the linked list, right? So if we look at the problem here, you're given this. So what does this node have? It has node data is equal to 3, and next is equal to that one. So I'm gonna call it 4. So 4 is a reference to the data head, which is probably pretty poor naming conventions, but that's the idea. So the problem here is if I were to remove this and just delete it, then 2 would not have, this is not going to be pointing to 4 because I don't have access to 2 at this point. So in order to do this, you would actually have to iterate from the beginning of the linked list all the way up until the halfway point before you get to 3. And then you would take this pointer and set 2.next is equal to 4. And then you would be able to remove 3. So that's probably the biggest problem with singly linked lists and linked lists in general is you don't have instant access time for getting each element and then editing it or change the list in the middle somewhere. But what you can do is augment your linked list so you have different pointers. You can have, let's say, doubly linked lists, which is the most common, where you basically have a pointer that goes back and forth from the node. So you'd be able to access both sides. So if we look at the problem before and we add doubly linked lists, so now we have ones that point back, then that makes removing node 3 a lot easier because you have now access to prev equals 2. So if you could just go to 3.prev.next equals to 3.next, which is basically saying 3.next right now is 4. So you're setting that, you're giving that value to 3.prev.next, which is 3.prev is 2, 2.next is pointing to 3 right now, but now I'm setting it equal to 4. So I'm skipping over 3, and that essentially removes 3 from the equation, and I can remove it. But you would also want to make sure that you edit 4 so that it's also pointing to the right thing. And these are just like very kind of complex, like there's like an order of operations you have to go through when you do these removals and like additions of nodes inside the linked list. You have to be really careful that you don't accidentally like remove something, or like have something pointing to the wrong thing before you do the next problem. So something I think I made a mistake doing this in data structures was if you like remove something, but you don't change, like, let's say I don't change 4.prev. Oops, I erased it. But if you don't change 4.prev to 2, then if you go to 4 back in the list, then you would go into like, you might have deleted 3 completely. So then that would just be like a bad usage of the list. You wouldn't be able to go anywhere from 3 and just like completely break your data structure, which is not ideal. There's like a couple of like intricacies you want to look out for when you're working with these. And so here are the runtimes. Let's see. So we have access, worst case. So O of n, just to be clear, is big O notation is like saying this should take less than or equal to this time. Pretty weird. Okay, Karina said something. Yeah, linked lists suck. These are just like really basic like introduction to things. These are really important for trees, which we will go into next. But yeah, linked lists are pretty useless. You'll see them in problems where they're like, they give you a linked list, but like you'll do something with it, just like understand like what to do, how to do it, and you should be good. But realistically, in a project, I don't think linked lists are very useful. Just my opinion. Anyway, so access time is going to be O of n because you could have to singly, well, actually both. And this is just because you don't know where the element is. So if I were to say, like, I want to find, it doesn't matter if like I want to find something at the index of the linked list, or if I want to find like a particular element, I want to like find which node is equal to 4 or something. You would still have to iterate through the whole thing to find it. And that's kind of like what makes these things really complicated and not that great, not very useful. Even in doubly linked lists where you can kind of like go from the back or the front, depending on whether if it's sorted or not, you still have to do like a whole traversal or like the runtime would still be O of n because that's only like reducing it by 2. And so n over 2 runtime is still going to be O of n. That's just because big O notation is amortized and blah, blah. You don't really worry about like the constants. Yeah. And then adding to the end is going to be O of n also, yes. Yeah, unless you have a pointer to like the tail, which you could have in like linked list. You could have attributes such as, well, you have to have head. That's the only one you have to have. And then you could also add size, which would be equal to like n, I guess. And then you also have tail. This is really useful. Tail is useful for doubly linked list, not so much for singly linked list because tail would just point to null and you just know what the last element is. So not very useful. Double. Yeah, linked lists suck, don't use them, but understand them. What did I say next? Stacks and queues. I guess we're not doing trees yet. Okay, so write that out. Stacks and queues are probably like one of the more like visualizable data structures, in my opinion. And you can do these with doubly linked lists or with arrays, array lists. Implementation, like your base class isn't super important, but let's just use linked list as like the base for this. So let's do stacks first. If you're given, let's do structure of a stack. So the idea of a stack is you have first in, last out. So basically you have a stack. Let's do the ring thing. If I put in an element, it'll go at the bottom of the stack. So that would be like stack dot add, or I don't know what the operation is. But like you would add your element, it would go to the bottom of the stack or the top of the stack, and then stack dot pop would take the top element off. So basically, if I had 1, 2, 3, this is the bottom of the stack, and I hit pop, I would take this one off, right? And that's what I would get. It would return whatever is in there, and I would remove that from the stack, and the stack would now only include these two elements. And if I were to do stack.add or append, I feel like that's not the name of the operation, but whatever it is, when you append it, it just goes on the top. So that element you put in first, in order to access it, you have to go all the way down and like pop every single thing off. So you need to like, this is a very like case dependent type of data structure. You want to look at your problem and see what is like the most efficient thing. Excuse me. Yeah. Stacks can be pretty useful. I guess the best idea or the problem that I see most is the towers of Hanoi, where you have 3 stacks. I believe everything's on one, and they're all like, they're disks that are like larger than the other, largest on the bottom. And then you want to move all of these over to the 3rd stack. And the rule is like, you can't, here, I'll just write it down. And the rule is you can't have a smaller disk under a larger disk. And you just got to understand like what order you want to move things in. So just working with stacks is usually kind of like a conceptual idea. You want to know like, what can you do? Like what does each operation do when you pop it from a certain stack? So I guess you'd have S1, S2, S3. Everything's in S1 right now. So your first operation has to be S1.pop, right? And then you'd want to add that element. So like S2.add S1.pop and so on. So that would say S2 is adding on this first smallest element, and you just continue moving things in a way that makes sense to solve this problem. I really recommend looking into Towers of Hanoi. I think it comes up in, I don't know if they taught it in data structures, but it's definitely like a problem that's good to know. It's not too complicated. There are a few like games online where you can just like test it out before you actually code it, just so you understand the problem, like the order that does this in the most efficient way. And so for stacks, your operations are very quick. They're all going to be O of 1. Oops. Pop, add. I don't know if it's add. But yeah, the operations are really quick because you're just putting it at the end of the linked list or whatever you use to structure it. So like we have this. This is the bottom of our linked list. If you add, it only adds here, or it pops from here. So typically, I guess you would use like a doubly linked list and have tail, and then tail.pop would just, or like pop the tail would just give you, and you set like tail to point to the element that was tail.prev before. And so doubly linked lists are a pretty good way to visualize it. I think it was also explained to me as in the form of an array, which gets a little bit complicated because in arrays you have the original set size, right? But if you keep adding things, you want to have to increase the size again. But the way you could do it in arrays, I don't remember this too clearly, was you can have your head point to index 0 at the beginning, and then you would have it loop around once you like pop things. Or maybe this was queues. Yeah, this is queues, my bad. But for stacks, I would recommend using doubly linked lists to visualize them. It's just really like easy to understand the concepts behind like where everything is going, because you see like you always have your head pointer in your linked list. I guess you'd call it stack, like stack extends linked list. So you'd have your head, and then you just make sure you have, I guess you'd want to have your tail to point to that last element, pop it off, and then see what it is and do whatever you want with it. The downsides to this are it takes a while to access things at the bottom. So you want to make sure there's like, that your problem really suits the data structure. Data structure is all about like understanding what the problem is and also finding like the right data structure to use with it. And it just so happens that most data structures like stacks, queues, linked lists, they're not that like widely applicable. They're kind of like unique use cases, typically at like easier problems. There's a lot of leak code problems, I think easy, mediums that deal with these. They're good practice, just like understand the structure. And these problems can also come up in interviews. They'll just ask you like like to explain these, or like, what does it do? What are the benefits of them? You know, there's a lot of variety. The other one is queues. Did I spell that right? I think I did. Queues is just a line. So think of like, if I was going to Costco and I want to get a hot dog, there are 3 queues, Q1, Q2, Q3. Each of them represents a window, right? And the idea here is first in, first out. Why did I do that? So basically, let's say we have each circle represents a person. This guy's at the front of the queue. So he's going to get served first. He's going to get to place his order and like get his stuff first, and then he'll leave, right? And then the next person will be the front of the line, right? So this guy leaves and this guy goes up to the front. That's how queues work. And then if you want to join the queue, you don't want to cut the other people, they'll be mad, right? So you'll join in at the end. So that'll be like queue.append. So you never, when your operations are always going to be like towards the front, towards the back. They're kind of unique, and that makes it a lot easier to like understand like what you're doing at each point. Like, I think it's not too hard to understand the order. You just be like, q.pop is going to be the first person. Q.add is going to be the last person. You won't see that last person again until he gets to the front. So I think these are more easy to visualize, I guess. And so again, if we were to do this in a linked list, let's do doubly linked list, you would have your pointer to the head and to the tail. So whenever you're adding, you would just do tail.next, which is previously null or none because there's no one after them. Tail.next is equal to new, like the new person. And then when you do head.pop or like stack.pop or q.pop, you're removing the head. So first thing you want to do is, so let's do, keep saying stack. Q.pop gets the first one. So you would want to do q.head equals to q.head.next. So that would point head to the next element, and that frees up the first node, but you also have to remember to set that new q.head. At this point, q.head is q.next. So q.head dot prev, in the case of a doubly linked list, is equal to none. You don't want to point to anything because now there's no one in front of them, right? And then I guess return. I guess you'd want to do something before that. Temp equals q.head, return temp. And that would give you that first node while successfully like removing all the connections between it and the next element. And then for tail.next, that's a lot easier. You just do next equals new, and then new.prev is equal to tail. That's not legible, but that's fine. Yeah, so it's pretty much the same operations, like the operation times. They're going to be O of 1 to pop and add. And basically these are stacks and queues. The idea is you don't want to be accessing, you don't want to have to access anything in the middle too often. And if you do, you want to make sure you don't need anything in the front or like that you've like gone through. There shouldn't be any like, oh, I need to go get something in the middle for some reason, but I still want to keep the structure. Like that's just a really costly and like, it doesn't look good for the queue or stack because you'll have to like destroy it and then rebuild it. And that's never efficient. Great. I guess pop, add. Yeah, so just like familiarize yourself with the ideas of these. I don't know if Python has actual queue classes, but like just understanding, maybe going through Python or Java to implement some of these classes is a good idea. Just like understand your implementation of the structure, why it works, and then also like how it would work when you import someone else's library and they use something that's based on like a linked list or a doubly linked list or stack or queue. And that'll really help you like pick the right thing for your project or whatever you're doing. Great, so I think trees are next. We are gonna talk about binary trees. And these are also kind of based on the previous node class that we have. So previously we had node that just has data and next. Now our new node class is going to have, let's call it tree node, T node. It's going to have data again. Now we're going to have child, let's call it left and right. This is because our tree structures are going to look upside down. They're going to be like upside down trees. From binary trees, that just means there are two, because binary. So you're going to have left child, right child, right? So this node is going to have, so let's call A, B, C. So node A is equal to node, and A dot left is equal to B. A dot right is equal to C. And the idea here is basically, for the most part, you only have these two ways to go. So it's a lot easier to traverse through, it's a lot faster to traverse through your entire tree. You can store a lot more data and access it in a way that makes sense, depending on how you implement it. The most common way to implement these is a binary search tree. Oh, you can also have like the parent, I guess. We can talk about that soon. Binary search tree is, the idea is you have the elements to the left is less than, elements to the right are greater than. So if we were to have element 2 as our tree root, we would have 1 and 3. And this is because 1 is less than 2. So when we added 1, we moved 1 to the left and added it there where it fits. And we added 3 over to the right where that fits, because 3 is greater than 2. So the benefits of binary search tree are basically you're able to sort through your data a lot faster. Sorting data is just a way to make it more legible and usable by whoever's using it. And that's the whole goal of like going through these things. So binary search tree, these are kind of like the more important data structures, although I haven't really seen them used in practice, which is weird. But so the idea here is you have elements that will, let's say you have a bigger tree. So here we have 8, is that 8? Yeah, no, 7 elements, not bad. In an array, how many is that? That's 7, great, cool. So in an array, this would correspond to the middle element. So it's over here. And this far left element is going to be your minimum element. So that would be first. While this is your far right element, and that would go over here. And I guess the interesting thing with trees is you can actually represent them with arrays. It does get a little bit complicated. It's a lot more easy with heaps, but that's also like a different type of tree. I guess we can talk about that a little bit. But for binary search trees, the idea, getting kind of off track. Okay, binary search trees, the idea is like, this is less than, that's greater than, and then once you have all that, in order to find like a certain element, let's say I want to find, okay, let's say this is 1, 2, 3, this is 4, 1, 7, 6, 5, 2, 3. Right, let's say I want to find element 3 from this tree. If I had this in a list, I would have 1, 2, 3, 4, 5, 6, 7. Whereas in the tree, I do 4, I have this, right? So let's go through our pathing for this. Actually, let's say we're looking for find 5. Right, I want to find the element that has number 5 in it. That's like the data I'm looking for. So if we go through our list first, we would have to go through every single thing, right? Because this is O of n operation. We just go through 1, it's not 1. Let's go 2, it's not 2. Blah, blah, all the way to 5. So that took us 1, 2, 3, 4, 5 steps, right? And whereas if we look at the tree, we go from 4. So our steps are 4. We'll compare that to 5. 5 is greater than 4, so we go to the right. We go to 6. We say, okay, 6, is that equal to 5? It's not. How does 5 compare to 6? 5 is less than 6, so we go left. And bam, we found 5. So it's 1, 2, 3 steps. And basically, 3 steps. And comparatively, it will depend on the situation, but again, with data structures, you're looking at amortized time, which is like average, not just like a specific case. We're looking at specifically when I look for the number 1 or when I look for 4, it would be really good for these trees because 4 is at the top, right? Whereas it would take 4 steps to get there in an array, I'd instantly get it in the tree. So obviously a tree is better. Not completely true, because you want to look at average case. Like if I were to find all of these elements like one at a time, like find 1, 2, so on, what's the total time for that? What's the average time of all of those operations versus the average time of finding all of them inside the tree? And you would see the tree is going to be faster because you see the most steps you ever have to take is 2 or 3, I guess. The third step, you would find it in this small example. And I guess the problem with data structures is mostly like you want to, like, it's great to visualize these things at small levels. Like I'm not going to draw a million like data elements, right? But these things have to be like extended and like extrapolated until you can like apply them to really large data sets like Excel sheets or however much data you have. Data is like so big now, you want to understand how you can apply these things to data and also get the best performance out of it. So what this comes out to, and I'm not going to do the exact math, but it's basically log n. That's the operation time it takes for you to go all the way down and like find a element. Like the height of the tree is going to be log n, which is approximately right. Like you'll see, look, there are 7 elements here, right? I think it's log base 2n. So that basically comes out to 3, right? Because 7 is pretty close to 8. 8 log, I don't know what the log math is. Basically log 8 is equal to 2 or 3 because 2 to the power of 3 is equal to 8. Yeah, that makes sense. So yeah, 3 is the most steps you'd have to go, and that's like a very close approximation. of worst case runtime for finding things. So adding elements is also going to take that same time because you have to go all the way down. You're not going to modify binary trees too much, at least not at this level. There's also like the auto balancing ones, which ensure performance benefit with binary trees. But provided you enter your data in like a certain way, this shouldn't be too much of a problem. So log n for access, adding, and yeah, what else? And I guess also removal, because removal is based on, everything is based on access, because you have to find the element before you remove it, and you also have to find the place for the element before you add it, right? So if I were to add the number 8 here, I have to go 4, 8 is greater than 4, 8 is greater than 6, 8 is greater than 7, bam, 8, right? So that would still take, everything's based on access here, and access is log n. Adding and removal are O1 operations, as we saw from linked lists, where you just add it to the node above it. And yeah, so the basic node class, I guess I went over it before, but there's also, so you have left, right, and child, or no, parent, not child, right, parent. And parent just points back up to the previous one. So this is just helpful for when you want to add, well, yeah, well, this parent can be helpful for like more complicated tree operations, depending on what you want to do. I'm trying to think of an example. I guess for auto balancing. So let's see, what is that called? Avl tree. Yeah, AVL doesn't actually like stand for anything that important. It's just like the inventors' names of this tree. But basically the idea is you have, your trees, and you don't want one tree to be off by more than one in terms of height. Because as you can see with these trees, you could have everything that's like going to one side, or like just being imbalanced, and that would actually increase the runtime, or like whatever operations you want to do on this. Because let's say I have a regular tree, I shouldn't do that. If I have a tree and I start with one is my minimum element, and I just keep adding. Okay, well, next I want to add 2, 3, 4, oops, whatever. And while this is based on a tree structure, like this is 2 is like 1 dot, right? So on. This turns out to be a linked list, which is not what we want. Like that's kind of ruining the purpose of implementing the tree in the first place. Like we didn't want to have those really bad access times of like O of n to traverse through the whole thing down to get to 4. The whole purpose of this was to have it balanced so that we could get these things faster than we did before in the linked list. So in order to avoid this kind of imbalance, we go to AVL trees, which will allow us, like their implementation just keeps the tree balanced over time. As you add things, it won't let, so let's say the difference here in height is 2, it wouldn't let that happen. It would try to reorganize the tree. I don't remember the exact implementation. I haven't done this in a while, but it would rotate the trees in some way that would allow them to have a height difference of less than or equal to 1, which is ideal. And that height balance just helps out the entire thing to be even, and your access times will be low, which is the whole point of the trees. Avl tree implementation is pretty complicated, I think. I don't have it memorized. I think Joanna, who teaches data structures, she goes in depth about these. This might be one of your projects. It's worth looking into. I haven't seen anyone like have to implement Avl tree in interviews, but it's worth like knowing and just like understanding that AVL trees are a thing. And I guess talking about them in interviews wouldn't hurt if they ask about trees. Yeah. And then some other tree-based structures you might want to look at are heaps. So basically the heap, a min heap, would basically be minimum element here is 1 as the root, and then everything that's below it just has to be greater than the minimum value. So each element is less than all the elements below it. So let's say I had 4 and 5. If I were to add 2, 2 says, okay, I'm less than 4, so I want to swap with 4 and move up. So these two would swap. And I have 2 and 4, and now 2 says, okay, I am greater than 1, so no problem. We can stay here. And heaps are a lot nicer to implement in arrays because you can have the indices as such. So you see 1, the root is always going to be at index 0, so it's 1. And then say left 2 and 5, and then we have 4, so on. This is nice because you see the index here is 1 or 0. So the index times, actually it's probably easier to say, let's just say this is 1. This is not completely true, but just like understand it. So to get the left index, all you have to do is multiply it by 2. And then you would get 2, and then right is times 2 plus 1. Right, because that's 3, and this works so on. Let's add a few more, just so it like makes sense, and you believe me. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 4, right? And that was 8, 9. That matches up. 3, 4, 5, 10, and 11. And this pattern just continues on. And if you want to implement a heap as an array in a really lazy fashion, you could do it. But visualizing it as a tree is really helpful. So it's just good to understand the basics of trees and how they work. Yeah. There's also like a thing called red-black trees that I don't know if they teach at school. I don't remember too much about it, but someone asked me the other day and I did not know anything about it. So that might be worth looking into. Anyway, I think hash maps are the last thing to cover. And this is like your golden hammer. You can pretty much use hash maps on everything, and it'll almost always be the perfect solution, or it'll be a key to like the perfect solution. And that's just because of how hash maps work. So previously we saw in linked lists, you have your nodes. And if we look at memory and the way, and like the program memory, each node is going to be at a different location. That's what makes them different from arrays. Arrays are contiguous blocks of memory. It's like your whole memory is going to be like a heap, like or a stack like that. An array would just cover all of this, right? So A is equal to 4. 1, 2, 3, 4. So erase that. 1, 2, 3, 4. That's A. A has to take up that entire block, and in order for you to create a new array, you'd have to move to a whole new size of A size 8. And you would have to point this to somewhere else with like a huge block of, 8 times whatever data type you wanted in order to establish A again. And what linked list did was it would take in that same stack, it would say, okay, here's node 1, here's node 2. And node 1 would have pointers in memory towards node 2. Like the reference would be called node 2, but it wouldn't have to be in the same place or same order. Node 3 could be up here and so on. Like it just gives you a lot more flexibility with memory, just like establishing it. And this is pretty similar to what hash maps do. So hash maps are kind of like arrays, but now you have your access keys and your values are all stored in different ways. So your key is going to turn into, so key is like an index, right? So instead of having to use like a number, so like here in the array you have A2 is going to point to index 2, right? Third element. So now your hash map, you can set things to be like whatever you want. So most commonly, I think in Python, these are pretty easy to understand. So they're called dictionaries, and you declare them with curly braces, and you have, let's say, key goes to value. And how this works is this is your key. So the key is basically what unlocks that the door to this value. You want to be able to access this value every time using that key. So key is usually going to be hashed or like turned into some kind of like access number or like memory location that you can use to point to wherever value is. So what a Hashmap does, or dict does, is it takes value and it slaps it somewhere inside your memory stack. So let's put value right there. And key is going to map to a certain like value that's going to point towards value. These are kind of confusing terms. Hashed key. Yeah. But the point of this is just like your access time is going to be really fast, because now in order to access value, you'd call dict key. And that gives you value immediately. That is O of 1 access time, because it knows key. It treats key as like the index, is like the way I like to think of it as, and it'll immediately know in dict this key maps directly to this value. And then same thing with adding things, say dict dot put, I think, or add. And then you'd want to add your key value pair, so KV, whatever it is. Again, this key is going to map to this value, and next time you want to access it, it'll also have O1. And putting it in there is also going to cost O of 1, because all it does is it takes this and finds somewhere to put it. Finds somewhere to put the V, and it just says, okay, next time you call dict K, that'll point to this. K will like go through like some kind of hash function that'll give out like a more complicated like value, and that value will lead to the pointer to this memory location, which gives us a V, and that's what we want, right? So this should also take O of 1. It's a constant operation, doesn't depend on how many data items are in the actual structure. So this is a really nice data structure to use, and it's pretty efficient in terms of everything. One of the negatives that you can have with this is clashing, or I don't know what the term is, but like when you have two keys that are the same, use the same key, you will actually add the values to each other. This depends on the implementation. I think for Python, if you do like dict key is equal to like a new value in V, it would just replace it. But I know there are certain implementations of hash maps where you will actually be appending it to a list inside that memory location. So this might be Java, because I think this is where Joanna taught it. So Hashmap, say we have your stack here. And originally I had a value in here, which maps to key, let's call it banana, right? And let's say somehow I have a bad hash function, and the word orange as a key also has the same hash key as banana, right? So I don't know what it could be. Let's say it's 23, right? Banana hashes out to 23, orange hashes out to 23. For some whatever reason, like my implementation of a hash function is not good, right? So now 23 is the hash key for value. So if I called banana, like, okay, that value is what I wanted, right? But if I call orange, I would also get the same value. And then, so that would give me the wrong value for orange, and that's not what I want. So I think one of the implementations for this was it would just add on to the bottom. So let's say value B, value O, and then you would just have, this is all like unseen. You don't really, under the hood, you don't really see this. This is not something you would implement unless you were implementing the data structure itself. value O would have to have like a certain thing that matches it to orange. Like orange would have like an identifier in the hash function that says like, I'm looking for like a certain element, or like when you hash it, it also puts the key in some, or the value in some way that's like says this maps to orange specifically, and then it would give it like certain tags that, you know, help identify it. And the problem here is if you have a really bad hash function, everything could be in the same block, and basically you just have another array where you have to iterate through the whole thing to find value T, value target, like whatever you wanted. And again, that's bad. You don't want to have too much like clumping. You want, the whole point of the hash map is to get that O of 1 instant access. So if you're having to go back to this array because your hash function is not good, and you end up with, again, O(n), or just not O one time, then you're kind of defeating the purpose of implementing the hash map, or using it at all, and you might as well use an array. Because hash maps can be pretty expensive in terms of memory, I think. Yeah. Let's see. What am I missing? Yeah, so I guess that covers most of those. Yeah, so basically the idea is you should always try to use a hash map for everything. It just offers the best access times, add times, pretty much any operation you would really ever want to use. It provides the best run times for that. There are certain times where you might want to use like a linked list, or, you know, array list, or whatever. It's not as common, and I haven't seen it be as useful as a hash map. Like it just makes so much more sense to use a really flexible hash map. You can set the type of your key and the type of your return value. Yeah, like hash maps are just like such a nice tool to use, and you should definitely like try to use them in your interview problems. Just see if they fit in somehow. They usually do, but also like it's good practice to like ask questions about the question, understand like what type of data am I getting, how much of it is there, do I have to worry about certain cases. You know, if the data isn't too big, maybe you don't need a hash map and you can just do it with an array, or some other data structure. It really just depends on what is needed, like what the idea of the problem is. So really quickly, I'm just going to go through this pun. I'm going to go through. So it was a pretty easy problem, I think, but I did it twice because I applied to 2 positions. Anyway, they had a list of numbers or dates, list of dates. So these would be numbers from 0 through 31, or 1 through 31, I guess. Right, and they wanted to see which days have appeared twice. I think it was like, this is a list of birthdays, you know, which day does a birthday occur twice, and return a list of that. So in terms of this problem, I think the first time I tried to solve it, I used a array, which would basically just be of size 31. And you'd have your indexes 0 through, I guess, yeah, 31. So size 32 array. And basically you could have 0 is useless, but 1, blah, 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 through 31. These are all like the indices. I shouldn't put that. And the way I decided to go through this is decided on using the array was because it's such a small set of data. You don't actually have to worry about your access times being too large, because, you know, like worst case, if I want to iterate through this, O of 31 is basically O of 1. Like that's not a very large number. If this was a list of dates like throughout the year, that could have been between potentially between 0 and like 365, which is still not too bad. But like if it was, let's say, over a decade, so 3,620, 650-ish, give or take a few leap year days, then you might want to consider, then I might have like considered using a different type of array list or data structure, like a Hashmap or something to simplify the problem. But when you're looking at really small numbers, it's pretty acceptable to use arrays, array lists, so on and so forth, without worrying too much about access times or like any of the other operations that give Hashmap so much power. So I don't think my implementation made much of a difference. And basically the idea was just like you iterate through X in dates, iterate through the list of dates, and then say, so X would be a number between 1 and 31. Say, so initialize this list to be all zeros, I think. List would give me the index. This accesses the index of that date that I have corresponding to each date plus equals 1, because that would be like the count of dates. And that's all you can do in the loop. And then for elem in list, if elem equals 2, then you just like add that to like another list that you would actually return, I guess. I think that's what I did. But yeah, I think for the most part, it's just like, it's nice to know the data structures, but also like you have to look into the problem a lot to figure out which data structure fits it best. And yeah, I don't know what else to say. Yeah, if anyone has any questions about anything we've like talked about, now is a great time to ask. You can put it in chat or just like ask it with your mic. Okay, someone left. What's the best code problem website to practice? I don't really know. I think HackerRank and LeetCode are the two most popular ones. Most companies send challenges through HackerRank. I think LeetCode has better problems, but I'm not too sure. I don't use them too much. Yeah, I would use those. Those two are probably like the most prominent, just because I think those are good to use just because they have like so much like name power and like people actually use them for, they deserve their popularity. People, companies use, they're worth looking into just so you're familiar with like the structure of it when you do go into the interview or technical challenge usually. Yeah, I would use those two. I think eBay does Codemy. What was it?
It's like code
eBay
signal.
sent me something through Code Signal. Yeah, Code Signal sucks. But Code Signal is one of the newer ones. There's a lot actually. I think there's also one Matt sent before, binarysearch.io. It's just binarysearch.com. That one's pretty good for like working with other people to solve algorithms. I haven't used it too much before, but I do think it's like a nice site to use. It kind of like keeps you accountable, I guess. I don't know. But yeah, LeetCode and HackerRank are definitely the top two. HackerRank is probably more LeetCode challenge. Cool, thanks for coming. Okay. That's a good way to approach online assessment questions. I don't really have like a great answer, but there's no thinking out loud element. That's true. I definitely had a hard time with online technicals so far. I think it's kind of just like being confident about what's going on, because sometimes companies will throw really easy questions at you and you're just like, this was like, I stressed out way too much for this. Like I did not need to spend so much time preparing for like a bunch of array questions. But I think the best way to prepare is probably just like going over like course material you might have done in data structures or one other class, like algorithms. That was pretty useful. If you've been in those classes, those are great. If you haven't, it's really a really great resource is geeksforgeeks.com. I will go ahead and I don't know, I should put in the chat. Geeks for Geeks. Geeks.com. Oh, it doesn't link, whatever. But yeah, Geeks for Geeks is pretty useful. I've definitely seen like a few of the implementations of certain problems on there. But in terms of preparation, I don't think there's like a ton you can do because you just don't know what they're going to put out at you. Like I think I applied to Roblox and they randomly select their problems. So I ended up with 3 dynamic programming problems and I rage quit because I hate dynamic programming. But in general, just like go in with like a bit of confidence and like don't feel too much pressure. I think they usually get like 2 or 3 hours. It's kind of like a lot. Definitely like depends on like what company you're going to, but I don't have great advice because I'm not good at it. But yeah, I don't know. Oh, here's, I think I've sent this before in like a different Slack channel. X and Y is pretty good with language stuff in case you're not familiar with like Python, C++, Java, whatever you want to use. And also it has like some algorithm and data structure stuff at the top, which is nice. I didn't actually use those before, but I think the site's pretty useful for just like reviewing syntax, because syntax is definitely something you don't have to worry about, especially in these online like take home technicals. Like you can just pull up like a window and look at whatever. And usually it's okay unless they have like a screen recording thing, which some places do, but yeah, syntax isn't like a huge problem for online technicals, but I think Andrew mentioned it on Thursday, like when you go in to do these actual like technical interviews, they will not give you like, you know, syntax pointers or whatever too often. Or sometimes you might not even be doing it in an IDE. So you just have to do it on like a Google Doc or on paper or whiteboard. So you just have to like figure it out on your own. Yeah, I don't know, it's pretty rough. Good luck. Yeah, no problem. Okay. I guess if you don't have any other questions, we can just end it. And I will go ahead and post this later. Whatever. Okay, I'm gonna stop the recording.